Hi everyone, today I'm here to talk about my project, decomposing sound using deep learning approach. I was inspired to do this topic because of my personal interest in music production, and within music production, one of the amazing things is to create sound that were previously impossible to achieve. With a synthesizer, we can create custom sounds that can be used in music production, sound effects for film and video games, and much more. Sometimes we need to decompose a specific sound for reproduction purposes. This can be especially important in music production, where a certain sound or instrument needs to be replicated and maybe added up with the producer's own flavors. By breaking down a sound into its original components, we can analyze and understand how it was created, and then recreate it ourselves. But what about using deep learning models in sound engineering? By training different types of neural networks on large amounts of data, it is possible to create models that are capable of understanding and generating complex patterns in sound. And also, it's important to evaluate how different models can be effectively used in different tasks according to the way sounds can be built, for example, additively or subtractively. By carefully evaluating these models on different tasks and understanding their strengths and weaknesses, we can make better use of these powerful tools in sound analysis. So, here's a bit of the outlines of my presentation today. First of all, I'm going to introduce the synthesizers, about their types, the principles behind, and how they actually work. Secondly, I designed several experiments to test different models on different tasks, and then its details on data sampling and pre-processing before put into the model. The next part will be the results of the fitting models and what could be interpreted from these results. In the final part, I will also demonstrate a demo task I deployed on my device, an Arduino Nano 33 BLE. So let's move on to the introduction of two types of commonly used synthesizers, the additive one and subtractive one. Additive synthesis involves creating tone color or timbres by layering up sine waves and manipulating the frequency, phase, and amplitude of these waves. This concept is based on the idea that tone colors can be created by combining harmonics at different frequencies, phases, and amplitudes. Much like the concept of the Fourier transform, the subtractive synthesis technique is the inverse of additive synthesis, and it involves making tone colors by filtering harmonic frequencies from complex periodic waveforms such as square, triangle, and sawtooth waves. And here's a graph for the illustration of this process. Following the right arrow is to put several sine waves together to compose a square-like wave, and on the opposite direction, as the blue arrow shows, is to make certain sine waves by subtracting certain frequencies over a square wave, which is subtractive sound making. Here's an example of how a piano-like sound can be made from layering up sine waves at different harmonic frequencies. And as you can tell, it's quite primitive and probably not the best replicate of a real piano. So how piano sound can be made via subtractive synthesizing? First, input some periodic waves. And then we apply some filters over them. And finally, we add some ADSR controls over the filters. Well, and also by adding all the other envelopes over all the other different modulators, we can finally get this piano-like sound. As you may see, it's probably not as simple as these only 3 steps shown here on the slides. However, the changes in the original sound right after applying the filter should be quite noticeable. And the next section is about experiment design. By going through this process, I want to find answers to some of these questions listed here. So the first one, is deep learning models capable of classifying periodic waveforms well at different pitches? So changes in pitches is because of frequencies, and that can be controlled by the MIDI input. Or is it good at telling amplitudes? Amplitudes can be controlled to change over time by ADSR envelope. So when the oscillation of wave attacks, for how long it decays, sustains, and when it will release. And in general, what are deep learning models most effective at in dealing with the audio data? For example, is it good at telling different frequencies? And the last one, maybe find out is additive or subtractive synthesizing techniques. So one of the two could be understood better in deep learning models. So I selected the 4 basic waveforms from my subtractive synthesizer, using them as labels, sampled them with different ADSR envelope over amplitude, tested them in deep learning classification tasks, and then putting in more samples with different filters applied on them, so change a bit on the harmonic frequencies within that wave, and then added changes in pitches to the samples, so their overall frequencies are changed. So for the data sampling, I first used Black Hole, which is an audio loopback driver that records computer audio play with minimal latency. And I recorded sound clips of 2 seconds at 16 kHz by edge impulse. This sample rate indicates the average samples per second, and this sampling rate satisfies the naked theorem for all my samples. The time span without data were then cropped from the samples. Around 80% of the data was splitted as training set automatically by data sampler on edge impulse. So the first pre-processing of sampled data was windowing. Windowing is a process of breaking up a continuous signal into smaller segments, which can then be analyzed and processed individually. One of the most commonly used window functions is the Hanning window, just like the bell-shaped ones on the graph to the right. The Hanning window is designed to reduce spectral leakage, which occurs when the spectral content of signal spills over into adjacent frequency bins. By applying a Hanning window to the signal before processing, we can reduce the amount of spectral leakage and obtain a more accurate frequency representation of the signal. When constructing windows for modeling, there are several parameters that needs to be considered. One of the most important parameters is the window size, denoted as K on the graph. This parameter determines the duration of the time span over which data will be sampled. By adjusting the window size, we can balance the trade-off between frequency resolution and temporal resolution. Another important parameter is the window increase, denoted on the graph as K minus Q. This parameter determines the overlap between adjacent windows. By using a smaller window increase than the window size, we can create overlapping windows, which can help to reduce artifacts and provide a smoother frequency representation of the signal over time. And within the windows, what happens is that fast Fourier transforms, or FFTs for short, are applied to the signals. FFT is an algorithm that allows us to transform raw audio data into a spectrogram, which is a visual representation of the frequency over time. By using FFT, audio data can be translated into images, and convolutional neural network models can be applied to recognize changes in pixel intensities. The FFT algorithm works by decomposing a periodic signal into a sum of sine waves with various amplitudes, frequencies, and phases. And it produces a graph with intensity over frequency, as shown in the blue-colored graph below. By transforming the data from time domain to frequency domain, different sine waves are possible to be departed from the original sound by distinguishing different frequency intensities within that wave. The parameter that controls the FFT is the frame length, which determines the duration of each analysis window, just like windowing in the previous step. And there's a frame stride, which determines the overlap between adjacent analysis windows, again, similar to the windowing concept before. Spectrograms images generated within these frames are then stacked up for analysis, as shown in the process to the right. This whole process that involves dividing data into several frames and operate FFT over them is called short-time Fourier transform. This process can further enhance the FFT algorithm to take temporal aspects into consideration. Finally, the FFT length, which I will introduce in the next slide. The FFT length, or block length, is a parameter that determines the number of points to be sampled on the signal. Like shown to the right, the point values sampled on the waves will serve as the raw input of the models. This parameter should always be a number of power of 2 in FFT processing. For example, 2 to the power of 8, which is 256 samples. It is important to note that the FFT length should be larger than 2 to the power of 1 within one periodic cycle to prevent downsampling. Downsampling can lead to a bad representation of the original signal, shown as the case 4 to the right on the graph. By increasing the FFT length, we can increase the frequency resolution of the spectrogram. And furthermore, an extra parameter that we use in the MFCC model, which will be introduced later, is the normalization window size. This is an extra step forward from MFE, another model, which takes into account the shape of the spectrum. And by taking into account the shape of the spectrum, we can obtain a higher dimensional representation of the signal. The next step, melt scaling, is to transform the linear scale in frequencies into a log form. This technique is based on the observation that human perception of sound is nonlinear in nature. Melt scaling allows us to imitate human perception. Melt scaling amplifies the scale at lower frequencies, making them more easily observable. Higher frequencies are considered less important and are therefore more ignorable. This is because human perception is more sensitive to lower frequency sounds, and the differences in higher frequency sounds are often difficult to distinguish by humans. And there's also a discrete cosine transform algorithm to further reflect human perception of audio, which I'm not going to elaborate here. So this